Okay, thanks, Jenny, and thanks everyone for being here. So welcome to this month's PPAI webinar. And our speaker today is Dr. Siegfried Schubert. Siegfried is a senior research scientist working at the Global Modeling and Simulation Office, also called GMAO, of NASA Goddard Space Flight Center. So he got his PhD in meteorology from the University of Wisconsin-Madison in 1983. And his research interests include climate variability, predictability, drought, hydrological cycle, extreme weather and climate events, and reanalysis. So during his stay at GMO the past several decades, Siegfried has been leading work on these subjects in the climate group. And relevant to these works, Siegfried has also organized many activities in the research community, and these include the leadership at the first NOAA Drought Task Force, organizing special collections on drought in Journal of Climate and Journal of Hydrometeorology, and also organizing international workshops to assess the current understanding of drought. So Siegfried is an AMS fellow, and he has also served as the editor for Journal of Climate. So during recent years, Siegfried has been leading the effort at NASA GML on diagnosing sources of model biases and investigating the impact of these model biases on S2S prediction. So today, he's going to talk to us about some of this work. So with that, Siegfried, take away if you're ready.
Okay, thank you, Highland. All right, so as Highland said, I'm going to talk about actually tendency bias correction. And a lot of this work has been published. 2 papers listed below, indicate that it certainly was a group effort involving my colleagues at GMAO. Highland, of course, not at NOAA, but Highland played a key role. Yehu Chang, Randy Koster, and Andrea Mola. It's not moving. There we go. So the basic idea behind tendency bias correction is to look at the errors the model makes very early on during the forecast. So the first few hours. Way before the errors have become nonlinear and interact. If you look at this equation here, that's kind of the basic idea. This is the equation basically satisfied by our data simulation system, where the tendency is equal to a part that the model produces, all that, the dynamics, physics, everything, and then a correction term that comes from the analysis increments. So, and it's this is the key term that we're interested in. So the TBC model, which I'll be talking about, is simply our normal regular AGCM with this additional correction term, which is now the average, long-term average of these increments. So average over many decades, actually. So this is a fixed quantity. It has, the only variability it has is we keep an annual cycle and a diurnal cycle. Otherwise, it's a fixed quantity. So that's, for all the prognostic fields, that's how we introduce this tendency bias correction. And so what I'll be talking about today is trying to answer these questions. Does TBC correct the long-term model bias? So again, giving the model only information, the sort of long-term average of the initial first few hour error that the model makes, how does that impact the long-term climate? And if it does, can we do more in terms of understanding where those corrections are coming from? What are the kind of important regions contributing to the corrections, really to help guide model developers where they should focus their efforts. And then I'll talk a little bit about the impact of TBC on forecast skill. And then at the end, I'll just say a little about potential extension of TBC, something we're working on now. So everything I'll be showing you is for the NASA GEOS AGCM. It's the same model used to generate Meritube, but here we use a lower resolution version of it, 1 degree versus a half degree using that. We've also done this with the coupled model, but I'm not going to talk about that today. So we'll be looking at a number of long-term simulations with the AGCM. They're all forced by the observed SST, roughly 4 decades of simulation. We'll be looking at a control, so the uncorrected model. That'll give us the estimates of the model bias. And then the run where we introduce this correction is TBC everywhere over the globe. And we call that TBC global. So we'll look at the impacts. How does that influence the long-term climate of the model? And after that, I'll show some results where we apply TBC to very specific regions. We divide the globe up into 17 different regions, and we apply TBC in just one of those regions, and again, run the model for 4 decades and see the impact. So we can look at separate contributions to the long-term climate impacts from these different regions. And almost everything I'll be showing you, those increments come from directly from the MERIT-2 history of analysis increments. And we can do that because this is the model that was used to generate the reanalysis, though not quite the same. As I said, it's a low resolution. And that turns out is an issue in some cases. And I'll talk a little bit about something called replay, where we get a better estimate of the increments that are more consistent with the model in question. So the next few slides, I'm just going to kind of give you kind of a qualitative, hopefully, sense of how well the TBC works. I'll give you a more quantitative assessment a little later, but this is to give you a feeling for how well it works. So along the left is going to be the bias of the model for different seasons, but actually I'll be showing the negative of the bias. And that allows a direct comparison with the right panels, which are the impact of TBC. So it's TBC minus the control run. So to the extent that those left and right look the same, that's giving you a good sense that TBC is doing the right thing, making the corrections to the biases. So what I'm showing here first is for the 250 millibar U-win. Again, these runs are a lot, it's almost 4 decades of simulation, so they're very robust estimates of the bias. So just kind of looking at it broadly, you can see that this TBC is actually doing quite a remarkable job of correcting these major biases we have. I want to point out in particular for June, July, August, we've had this long-standing problem of the North Pacific jet being stunted, and has all kinds of release all kinds of problems with, this jet is very important for acting as a wave guide for Rossby waves impacting North America. And that's been just a big issue for us. And this corrects a lot of that. And this is a bias which is not unique to the NASA model. I've seen it in CAM and a number of other models. So it's a very kind of ubiquitous bias that has been very difficult to correct. The other thing I want to point out is we actually tend to do worse during DGF, during the winter seasons. You can see in the Northern Hemisphere, we're not getting as much of that correction as we would like to see. And that is, I'll come back to that later, and that is partly a problem with how we compute the increments. Anyway, so the bottom line is we tend to do pretty well and tend to do somewhat better during the warm season than the cold season. This is just another example. This is 2-meter temperature. Again, just kind of looking at comparing the left and right, you can see we have fairly large biases in the AGCM, especially during winter and summer. And these are, to a remarkable extent, and again, I'll quantify that later, are corrected in the TBC run. Now, I'm also looking at precipitation. Here's an example of a quantity we don't directly, we only introduce these increments to the prognostic field. So this is something that the model has to do on its own, suggesting that with better input, it's also giving us better precipitation. So again, overall, pretty good. Again, I'll point to one in particular bias during June, July, August. We've had this long-standing bias of being too dry in Central Great Plains, and the TBC acts to correct that quite a bit. Again, I'll quantify later, but that's another example of a model bias that's not unique to the GEOS model. Many other models have this problem with insufficient rainfall over the Central Great Plains. And just one more slide. Taking a little time here too. So just another example of getting more into the weeds of quantities which are further from the actual prognostic field. So cloudiness, looking here at June, July, August, clearly don't correct everything. This is all with respect to Mera too, by the way. But if you look at, say, over North America, the TBC is kind of doing the right thing in terms of adjusting correcting our cloudiness biases. And then even if we get into like the surface fluxes, latent, sensible, long wave and short wave, all these sort of more, things that are more removed from what we're directly correcting are also being corrected. So, so the question is, why is this? Why are we doing pretty well with the TBC? And so there, I think basically two reasons. One, certainly compared to the previous generations of reanalysis, we're actually getting pretty accurate estimates of 6-hour forecast arrays. Some of you may be old enough to remember the early analyses where data insertion was just, you couldn't believe anything, the first 12 hours, because the model was just kind of adjusting all over the place. So that's really a big change and allowing this kind of bias correction to be successful. The other is the fact that TBCs are small. So the corrections that are being made are not particularly large compared to the physical quantities. And that's what I want to show on the next slide. So here we're looking at again, this is along the top here, Mera 2, for example, satisfies this equation. The long-term mean of the tendency is the sum of all the models, dynamics, moist processes, and so on, plus this TBC, this analysis increment. And here is what those long-term averages of those various terms look like. Again, that point is not to look at the details, but sort of the amplitude of these quantities. And it's the sum of these 6 quantities, which is the total here on the lower left. So that's kind of this subtle, difference, sum of all these different terms, and that's what TBC is balancing here. So that's the middle panel. Those are the increments that we're introducing to the model at every time step, and the sum is, by definition, 0. So that's really an important part of this, I think. We can also look at another quantity, the moisture. Whoop, let me go back. So I'm sorry. So this is the moisture. Same thing again, where the physical terms are quite large compared to the residual and the TBC, the part that's making those corrections. So that's really kind of an important result, and it gave us some confidence that things kind of behave a little bit linearly. That because these adjustments are so small, that we can actually decompose the results. So we can look at the impacts from different regions of the globe. So these are the 17 regions that we've divided things up to. There are these 5 zonal bands, the tropical band, 2 mid-latitude bands, and the polar bands. And then for the Northern Hemisphere mid-latitude band, we further divide that up into 6 subregions, and also for the tropics, we divide this up into 6 subregions. So much of what I'll be looking at next focuses on this NM region, this northern mid-latitude region, and the various subregions, and in particular, I'll also be focusing on this NM5, which is roughly the North American region. And we'll be looking at, so how much do the various contributions from these other regions contribute to this region, to the NM, to the corrections we make in the NM region, and then within the NM region, how much of the correction we make to NM5, to the North American region, come from these other regions. So a little bit complicated, but the idea is kind of we look at how one area impacts another area. So this is now an example, again, going to the 250 millibar U-wind. This is for June, July, August again. Your upper left is again the negative, the bias. And in the middle here, this is where we apply TDC only to the northern middle latitude region. So we don't make any correction anywhere else. We only do that here. And you can see a lot of the correction that we make to the bias is simply coming from that NM region. So all these biases we have in the tropics, our precip biases, really don't play a role. We're kind of protected by the easterlies. The easterlies don't let any of that, all those biases significantly impact what's happening in northern mid-latitudes during the summer. And then we look at the separate impacts from these subregions. And the key point here is that much of that correction is coming from this region centered over Tibet. And I'll be coming back to that in a minute, or why that might be. But you can see that a lot of that is just coming from here. And then if we do add, there's some, not insignificant other, for example, just upstream of North America that plays some role. And if we add them all up, that's what we get here. So this kind of reproduces the result we get from the full correction to the full NM region. So this is what I was talking about, the linearity. We're not really double counting a lot from these different corrections, that things kind of add up. So it really facilitates our interpretation of these results as coming from these separate regions. So this is now quantifying that, basically, where we use this normalized spatial inner product. And we ask this question of how much of the correction from these different regions is contributing to the correction over the NM region. So the top row here is basically telling us that this is now the impacts from these different zonal bands and how they contribute to NM, the NM region. And the key point here, which I tried to make before, is a lot of that is local to the NM region. So these other, especially, for example, we just saw during July, August, there's almost no contribution from the other regions. It's not true for DGF, where we are seeing impacts from the tropics. And again, I'll come back to that later. And then the bottom row is then asking, well, how much within the NM region is contributing to the TBC, to the subregion of NM. And again, here, the key point is a lot of that is coming from this Tibet region. So the Tibet region is really key to a lot of these improvements that we see. So next, so everything I've talked about so far is kind of looking at how one region affects another, but I haven't really quantified the impact on the actual bias. And that's what we do here. Now we're going to focus on the biases over North America, this NM5 region. And we're going to look at how the contribution from these various regions to the bias correction in the NM5 region. And here I have two bars for each result here, and they're just two different sources of validation. The lighter bars are where we validate against ER5, an independent reanalysis, and then the others where we actually look at the bias with respect to station observations, which is GHTN for 2-meter temperature, and it's GPCP for precip. So just looking at the upper left first, the first thing to see is that if the corrections in the NM region and account for roughly 60% of the total bias in the NM5 region. So we're with this TBC applied only to the NM region, we're correcting roughly 60% of the 2-meter temperature bias in the AGCM. The other important thing is that those corrections are not just local. So this is when we make the local corrections, so the correction only in the NM5 region. And these are two of the key upstream regions, the NM4, which is just upstream of North America, and then the Tibet region. So the key point here is that 2/3 of the correction is not local. It's coming from areas that are remote to the North American region. So that's really an important result for developers if they're trying to correct the temperature bias over North America. If they just do it locally, fixing or tuning the land surface model, that's not going to give a correct answer. Because 2/3 of those biases are coming from other regions. So that really is an important result. Looking at DGF, that's not the case. First of all, we only correct on the order of 30% of the bias, and all of it's local. So that's quite a different story. Looking at precip, it's kind of the same. Here we correct less than we saw for 2-meter temperature, on the order of 50% or so. But again, a substantial part of that correction is coming from upstream corrections, and only part of it's from local. DGF, again, it's even less, in terms of how much we correct. And the other point here is this issue of double counting, which I mentioned earlier, that especially for precipitation, we find that it's more difficult to interpret the separate impacts because you kind of double count corrections you make in one region where really shouldn't be corrected because they come from problems that occur in remote regions. So that I'll come back to that a little bit more later in terms of why that might be occurring. So let me now just say a little bit about why Tibet is so important. If you look at the increments, this is for June, July, August, and looking at the temperature increments. And the key point is, so this here is the this NM5, NM2 region. And the key point to make here is that while these TBCs tend to be small, they're actually not particularly small over the Tibet region. And they're fairly substantial in terms of degrees per day, several degrees per day. So what this is saying, the reanalysis is really trying to cool this area, but the model is much too hot here. And what we do is, so we introduce effective cooling in that region. And what I failed to point out is we also correct the precip. We tend to rain way too much there. So we're both reducing the precip and introducing directly a temperature cooling. So the effect of that is here, lower left. So this is already basically what we saw in terms of the winds, but here I'm just showing this in terms of the eddy stream function. Again, showing the impact on the jets. And so the impact of that TBC in that region is hemispheric. It's really not local. And just to, so there's kind of a dynamical response to that. And to really emphasize that, we've done something very simple. We've taken a stationary wave model, introduced an idealized cooling in the Tibet region, and this is the response we get to that. So really, I mean, that's pretty convincing. I think that what we're really seeing here is a sort of dynamical response to the heating, which is generating a lot of these biases, and it's impacting not only things locally, but certainly also over North America. A lot of the precip biases we've had are being corrected by this TBC. So let me now briefly return to the winter. So we've had this kind of negative PNA bias in our AGCM for as long as I can remember. It's just been something we just don't seem to be able to get rid of. So many different improvements to the model, but we continue to have that bias. And so it was particularly disappointing that we didn't do better with this TBC. So, and we struggled with this for a while, and it turns out, as far as we can tell now, it's sensitivity to how we, the fact that the model we use is a coarser resolution than the one in Mera 2. And so the increments aren't quite appropriate to that model. And so instead of generating the increments, using the increments from the reanalysis, we actually regenerate them through this process called replay, where we take the model we're interested in, and then we run it, compare it every 6 hours to an existing reanalysis, compute the corrections, rewind, and then continue on. So it's kind of a bootstrapping process which generates increments which are more consistent with whatever model you're interested in correcting. So that's really some good news. So you don't need a model that's being used in reanalysis. You can take any model, any reanalysis, and generate these sort of increments for doing this sort of correction. So if we do that, now this is actually a newer version of the AGCM, but as you can see here, the bias is almost identical. This is again showing that despite so many different improvements, we can't seem to get rid of that this sort of negative PNA bias. And now this is when we have the correct increments, and this is the impact of the TBC. So now much better. I mean, these look very similar. So we're getting this ridge and improving the trough. So we're much better impacts. And now we're also then looking, well, where the contributions coming from to that, to making these changes. And so we look here, this is the impact from the NM region. So just like we saw before for June, July, August, some of that correction is really local. But now we see, in fact, that the tropics is playing an even more important role. So a lot of these biases are coming from the fact that we, in the wintertime, we're not protected so much by the easterlies, and our precip biases are having a big impact. So that's really good news. The bad news is that if we look in more detail, we see a substantial part of that bias correction is coming from the Indian Ocean region. So that means, we know in the Indian Ocean, the models, our HCMs are just not appropriate. They're not responding. These are SSTs that are generated by the atmosphere. So there's no reason to expect the model to be responding properly to that. So I think we're kind of getting this correction for the wrong reason. And my feeling now is that AGCMs shouldn't be getting this particular bias right. That it's just not appropriate, and really need to be running coupled to get those stationary waves right. Okay, so now let me turn to a forecast scale. So here we've been focusing on June, July, August, and we're running with observed SST, so we're not really, of course, looking at impacts of SST, but so we're looking at sort of sub-seasonal forecast scale during June, July, August. Again, they're not true forecasts, they're hindcasts, and we're giving them the right SST. But anyway, so we've run a fairly large number of control hindcasts with the uncorrected model. We've done this every day from May 1st to June 30th, running through August of these years, so 18 years of forecast hindcasts. And that's to be compared then with the TBC hindcast, so the model which has been corrected with this tendency bias correction. The only difference here is that, so we don't bias ourselves with this correction. We actually, for whatever year we're focusing on, we don't include in the bias correction the contributions from that year. So we're not biasing ourselves by including information we otherwise wouldn't have. So so before I actually show the results for the forecast, it turns out everything I've shown you now has been for the mean state. It turns out we also correct the transients, which is very hopeful as far as potentially improving a forecast. So this is just now along the top here is the control minus merit 2 in terms of the momentum E prime V prime, the energy V prime squared, and the moisture fluxes. So the color here is just indicating the biases we have with respect to air in these different fields. And along here is the same result, but for TBC. And to the extent that the colors here are weaker, not as strong, you see that we are correcting the transients as well. So quite substantially, for example, for the fact, we have these negative biases in U prime, D prime, we're really doing quite well in correcting these. So again, TBC is doing more than just this simple empirical correction to the prognostic fields. It has no, these are daily transients, so it doesn't directly impact anything through the time scales that it has. It's just basically a fixed force. So anyway, so let's go to forecast scale. So this is kind of looking kind of broadly. We're averaging over large regions, and we're looking at, along the top, we've decomposed the total RMS air into a part that has the drift removed, so the kind of the random part of the RMS air. And then this is the drift part. So this is the part because, we're improving the drift, obviously. So this, we really need to separate that part out. There's another part I'm not going to talk about now, but it's the kind of the perfect model part of it, which is the forecast compared to its ensemble mean. I'm not going to talk about that. I'm mainly going to focus on kind of the random part of the air, the black curves, and the drift, which is what we're kind of directly impacting. So the top here is, again, looking at the U wind average over the entire northern hemisphere. If we look at the green here, the dashed is for the control and the solid is for the TBC run. So this is kind of what we'd expect to see, that because we've definitely reduced the biases, so the drift there's still a little bit of a drift, but it's nowhere near the type of drifts we're getting in the uncorrected control run. Now the disappointing part is the black curve. I mean, the impact on sort of the non-systematic part of the RMS air is basically nothing on this in U250 and this large region. So in this sort of average sense, it's kind of a disappointing result. This is now looking at V250 and looking at a smaller region. This is kind of the North Pacific region, kind of the edges here of Asia and North America. Again, we see some contribution from the drift, but again, very little impact on kind of the non-systematic part of the air. This is now the same result, but looking at for the same quantity, but looking at correlation. Again, you really have to stretch to say that maybe a small improvement here after day 10 or so, between day 10 and 20, but you're really getting very close to zero correlation. On the right is looking at the correlation spatially. So this is the skill for the TDC run, and this is the skill from the control, and this is the difference. So again, nothing dramatic. It's kind of where we expect to see some improvements along the jet. But again, they're significant, but nothing to write home about. So getting a little desperate to show some impacts, we try to think of, well, we're correcting the jet. That's kind of one of the big impacts. So, and we know that the jet is acting as a waveguide, and that's just kind of illustrated here. If we look at 1-point correlations with the V wind, you can see here, people at 10 to 30 days and longer, you have these Rossby waves here that are really, being confined by the jet. So the hope is that, we are doing something in terms of these Rossby waves and helping in terms of their propagation and impacts on North America. So that's what we look at here. This is now looking at 2-meter temperature over North America. This is the impact. So that's the skill from TBC minus the skill from control. We can see some positive values here, but again, nothing dramatic. And this is now if we we only take those forecasts for the leading rotated UF, so the leading Rossby wave and that's what's shown down here on the lower left. This is kind of the leading mode that we find. You can see that it's confined to the jet. And this is if we composite the impacts of this mode in terms of 2-meter temperature, you can see it has big impacts in this sort of central North American region. And that's really where we see the impacts then when we look at forecast skill. So it's really sort of consistent. And we actually looked at the skill of this mode, and it definitely is improved in terms of forecast skill. So that's so the message here is, the impacts and skill are not dramatic. You really have to look and, find those times when we can expect, the type of corrections we're making to the bias have an impact. So finally, the last thing is, looking beyond is a very simple thing, just putting in this mean correction. Can we do better than that? Since that doesn't really directly impact transients, even though it does, but there's no guarantee it does. And certainly there's no guarantee it impacts skill. So another sort of an extension of that is where this correction, this increment, we actually model that not just as a constant term, but actually as a linear, sort of state-dependent component to that. So that in that way, we actually can minimize the tendency error that we're making. So it should, theoretically have an impact on the time rate of change, and therefore perhaps have a more direct impact on forecast skill. So anyway, so that's work in progress. It's much more difficult problem than what we've done here. We have more parameters to estimate, getting robust. Chang has been working on this, and just getting robust estimates of the alphas is a real challenge. We really could use a lot more data to get that. And now, because we have this state-dependent term, there's a risk of the model blowing up, and we've been able to control that for the most part, though we see some issues with that as well. Anyway, that's pretty much it. Conclusions, hopefully I've shown that this TDC, very simple correction to the model has huge impacts on biases. We've had, decades of model development which we hadn't been able to improve. And actually now we've had a version of the model where we've been able to correct some of these problems over Tibet, and we do see now finally improvements in the jet and some of the biases we have over North America. It seems to work better in summer than winter. I've said, this is partly because of the role of tropics, and we haven't, we've used increments that are probably not quite appropriate to the model, and when we do that, we do see better improvements. That this TBC kind of extends across not just the prognostic fields, but a lot of the other quantities of interest. And then doing this regionally is really a nice tool, even if you're never going to use this in kind of a run this in forecast mode for operations or anything like that. It can really be a useful tool for developers in terms of understanding what matters for these various biases. This issue of double counting is something we're still trying to understand. For example, what I showed you for DGF, where the tropics and the latitudes have an impact. I suspect, and there was some, I didn't emphasize, but some double counting there. That's because ultimately the errors are in the tropics, but the tropics affect the jets, which then improve the stationary waves. And so when we do that correction, not only in the tropics, but also in the latitudes, we're kind of, the mid-latitude correction is probably is for the wrong reason. It needs to be corrected in the tropics. So that kind of double counting seems to be particularly a problem for precip and during the winter. And again, north forecast scale is very modest, and it's something that I think it just reflects the fact that on average, the sub-seasonal forecast scale is never going to be greatly improved, no matter how good the model gets. And we really need to focus on kind of these forecasts of opportunity where there is potential for greatly improved scale, just because we know things are dynamically active, or the land conditions have large amplitude and things like that. So that's really, I think, a reflection of that. And can we do better? We are looking at this linear state-dependent term. I'm not sure how much more we're going to do with that, just because it's probably not something we want to pursue in terms of actually using that in a sort of operational sense. But it's kind of a nice theoretical work, something to look at and see if that has an impact. So that's it. Thank you.
Okay, thank you, Siegfried. Does anyone have any questions for him? If you do, use the raise your hand button, or you can type it in the chat box.
Or we could just speak, right?
Yeah, go ahead. This is a small group, so I think if you want to do a little free-for-all, that's fine.
Okay. Sig, that was a very interesting talk. I have a lot of questions, but I'll just ask one for now and come defer to people. But, well, for start as a comment and a question, the comment is that Tim Del Sol, did a study on something like this years ago, which I always like to remind people when they're doing this sort of thing. I don't know if you're aware of it or not. Where he was basically looking at the difference between doing a a priori nudging of this type, trying to improve the mean base state versus a posteriori removal of the bias. And he basically concluded they got the same, they generated about the same thing and didn't improve the skill. So I think this is kind of consistent with the point he made with a simpler model years ago.
Yeah, no, I remember that. I think, part of this, as I said, is, ultimately it wasn't really to use this operationally in any way, but to help us understand, that's something you can't really do up posteriori, is where those, what's important for those corrections, to how do you, and basically to help you understand what's important in terms of correcting those biases. The other thing I should mention, there are actually kind of two time scales involved here. There's one time scale that is how quickly biases play a role. So that's kind of what you saw, kind of the drift, how quickly the drift develops, and the other two. So at what point does the bias actually bite you, in terms of forecast? The other time scale is just the the overall predictability time scale, and so part of what's happening here is that it actually takes 10 days or so before those biases come into play, and so by that time you're ready. In terms of the subseasonal, you're ready at kind of a lower end of kind of the inherent predictability. So that's partly why you don't.
Have you looked at like a weeks 3 and 4 scale? Because I'm going to bet that it won't be any better.
Yeah, definitely. I agree with that.
I think, and this is a long conversation, but I think this has to do with the nature of trying to do these corrections, that they're fundamentally non-conservative, and eddy interactions, eddy activity conservation is intimately tied up with how the base state is forced in the physical system. So that's always my view of this sort of thing, that you can't improve the skill much that way. But having said that, I'll contradict that and ask whether you've thought of doing, kind of, rather than going to a very complicated state-dependent correction, that you think maybe a little more in terms of a case-dependent correction. So for example, during the winter, I don't know what version of the GMAO model you're basically using, but I know that the one that was in the NMME, when I looked at it, had one of the worst errors in the Western Tropical Pacific at leads of as short as a month because of the ENSO shift to the west. And that shows up in precipitation errors there as well. And I would not be surprised if it showed up in a downstream error. So I'm just wondering if you could try something a little less ambitious, but a little more ambitious than a mean state correction, to see if you can change, maybe improve some dominant mode of climate variability, and then see if that has an impact on other quantities downstream, including the skill.
Yeah, that's a good suggestion. We hadn't really thought about that. I think part of the problem with the this is all AGCM. So the coupled model, we've also done bias correction for that, and it seems to work pretty well. But the coupled model has just very different biases. Partly what you're talking about, the double IPCZ, the just excessive precip, the cold tongue extending too far to the west, that's partly, I think, what you're talking about. So those are errors that we don't correct very well.
I don't think it's a couple model error, though. I think this is the atmospheric model responding incorrectly to SST. And you see the error up so quickly, it's got to be in the atmospheric model that's driving the error, because presumably at some level it's responding to the correct SST at t equals 0. You're basically initializing it right.
Right.
And the fact that the error developed so quick, and if you look at the NMME runs and look at the daily data, you can see some of these errors in some of the models. I don't know if the NASA model was one of them. The wind errors develop in the first week.
Oh, okay.
You see them develop very rapidly, and so it might be that a nudging, kind of some sort of ENSO related, say, or SST related nudging in the tropics, where you determine kind of a mean error, or a linear regression error is probably what you might want to do, because you might need to have some sort of amplitude weighting.
Yeah.
That might be at least worth exploring, rather than going through the whole much more complicated state dependent error.
Yeah, that's something we might try. Yeah, thanks.
I do see a couple questions from people who have been waiting patiently, raising their hands. John Nielsen Gammon, do you want to go ahead and ask your question?
Okay, yeah, sure. Thank you. So are your corrections right now, they're seasonal mean biases?
They're actually different for every day of the year.
Okay, so in that sense, you already have it being state dependent with a dimension space of over 100.
It knows about the seasons and the Dynamic cycle, but it doesn't know about the state of the atmosphere. Yeah.
Okay, so maybe 4 or 5 dimensions. I was just wondering what dimension space are you using for going on to what you're calling state dependent biases?
Yeah, I mean, I'm not sure how how to interpret that. All I can say is then we have double the number of parameters we have to estimate. However many we had to estimate for the bias PDC, and now we have to estimate that for this term that involves the state itself. So this alpha X. So it's a lot. So I mean, so there's a question of how robust that is. We only have 4 decades of the analysis.
Yeah, but I'm wondering what I mean. You can do a low order state dependent bias correction by having a correction that depends on leading mode of variability, for example.
Right. That's kind of what I guess Matt was suggesting, some kind of conditional on some phenomenon and so or whatever. So yeah, that might be a kind of a compromise. Perhaps what we're trying to do was too ambitious. The other thing I forgot to mention was just this difference between AGCM and coupled. Our initial attempt for the coupled was we correct the AGCM and then run it coupled, and that was just a disaster. You really had to do the correction, do this replay within the coupled model, and then we still only correct the atmosphere, but we had to have it know the ocean was there, and the biases for the coupled system are just different. Even as Matt was saying, things happen pretty quickly, but in the AGCM, but that is enough to somehow the model knows something about the ocean changing in the first few hours that impacts these estimates of these increments. So that's kind of just a sidelight.
Yeah, thank you.
Question from Haiyan.
Hi, Siegfried. Really appreciate this work and presentation. And I just have a question about, because as you mentioned, there is a problem of double counting, and you showed you try to separate your domains in to look at which domain is more important. But I just wonder whether you also thought about separating physics from dynamics, or just as you and Matt just discussed, to look at some particular problems, such as, say, if we improve the precipitation associated with MJO or the MCS over the Great Plains, how much error it can reduce, things like that. I just feel like, in general, it is hard to separate the cause and effect if we apply the bias correction too broadly, and maybe this technique can provide more insight if we just focus on particular processes and the domains.
Mm-hmm. Yeah, I think you're right. I think this could be dissected in different ways. I mean, we have done where we just corrected, this is something Highland actually did, separated, just corrected the winds, or just corrected the temperature, just the moisture. And at that time when we were doing that, we were focused on trying to understand this impact of Tibet. And if I remember correctly, it was primarily the temperature part of that. So making the temperature correction was critical, as you know, and as we showed, you know, from the stationary wave model results, that it's really it's excessive heating, you know, it was just too warm over Tibet and too much precip, and that was so making that, you know, correction to the thermodynamics was critical. That in terms of improving the jet and all the downstream effects, you know, which I was talking about, so that better jet, better wave guide for the Rossby waves and you know, their transients, and that had the downstream improvements to the precipitation of the Great Plains. So I mean, we've kind of looked at this kind of from a process point of view, but I agree, you know, maybe we could do more and dissect that just in different ways to become, you know, to get even more at exactly what, you know, the processes are that are contributing to these biases.
Can I add just a little one small questions? And I feel like this is a very general question. Say the modeling in the last 2 decades, maybe like most of the efforts in modeling are kind of poured into the physics part, not the dynamics part, and the high-res models. And do you have anything to say, or like how this process can encourage or discourage our current investment like trend in modeling?
Well, I mean, at GMAO, we have a very strong effort, you know, looking at very high resolution models. And so that's coming along, and I'm really 100% behind that. But, you know, they're going to ever higher resolution. They're kind of taking over, you know, it's no longer the case where you just, you know, have to worry so much about specific parameterizations if resolution takes care of that for you. But I still think, you know, for a lot of problems, you know, climate problems, it's going to be a long time before those kind of models are going to be used routinely to run. You not only have to run long times, but multiple ensemble members to really get at the biases and not only the mean, but in the transients. That's really an important part of you know of trying to improve models. That you know, a lot of the problems we see in you know, our seasonal forecast models being too confident, under dispersive. That's ultimately, you know, even though people, you know, focus a lot on how you initialize, a lot of it is just the models are just not variable enough in some cases. That they're just not dispersive enough, and it's tied in with the physics. And so so anyway, I'm just kind of rambling, but I'm all for going to this very high resolution, but I think there's still a lot that can be learned and a lot to be done, at least in the climate context.
Hi, Siegfried. This is Sergey. I have a question. Have you looked up, so when we tried the same technique in the Navy model, we discovered that the bias, well, it's not a surprising discovery, but the bias saturates. So the bias you observe in the first 6 hours is not the same you'll be observing in, you know, day 6. Have you explored this forecast lead dependent bias correction?
No, and we all we've done, as I said, is effectively use the information we get from the reanalysis. So that, you know, before we did replay, that was kind of there for us just to use. So we haven't considered that. And in some ways, you want to do this as early in the forecast as possible, and that just because you don't want areas to start interacting, you know, and waiting even longer. You know, things become nonlinear. So the closer you can get to t equals 0, I think the more likely you're going to make corrections that are reflective of the model deficiencies, and kind of making kind of adjustments to the physics in some way. As you begin to wait longer into the forecast, that's no longer going to be the case, and that kind of models things, and you know, you're dealing with errors that haven't had time to interact and so on. But
Do you still apply, when you run your 60-day forecast, do you consistently apply the same corrections through all 60 days that's modeled on the first 6 hours?
Yes, it never changes. That is, you know, it's just like we do for the long-term simulations. It's one value. never changes other than, the fixed, annual and diurnal cycles.
Do you see degradation in some biases, like if or you always see improvement in biases?
We haven't seen really much in terms of long-term climate. We haven't seen too much in terms of actually increasing the bias. I don't recall none. I mean, it's certainly possible that in some regions we're doing worse, but it's not. I'd say 90% of the corrections are in the right sense. But I'd have to look again at some of the results to see that.
And another quick question. So you mentioned when you were doing it in a coupled model that you have to do the replay to calculate the proper correction.
Right.
Does this suggest that when you do the replay, your average correction looks different than the average analysis correction?
Yes, definitely. I didn't expect this. It was a complete surprise to me. I expected if we corrected AGCM, the couple model would be fine, because we're just looking at the first 6 hours, but it just didn't work, and the couple model would just go crazy. The biases would be larger, so we actually had to run coupled so that the increments could be computed in a way that the model sees what the ocean is doing. So I understand why.
Oh, okay. So I guess you didn't have a weakly coupled system. So when you were applying the average analysis correction, it was coming from a purely atmospheric run. Is that correct?
Everything we correct is in the atmosphere. We don't correct anything in the ocean. Even when we run coupled, when we replay coupled, we don't make any corrections to the ocean. Everything is in the atmosphere. And yet, in order to get the right increments in the atmosphere, we need to do replay coupled, so that during the replay, the model is seeing what the ocean is doing. And that, I think we need to explore more. I think there's some really, useful results there in terms of trying to understand, why the coupled model tends to go, get these double ITCZ, things that actually develop also very rapidly, like Matt was saying, that there's something that's going on in the coupling that is perhaps not right very early on in the forefront.
Or I'm not sure if, I'm not convinced it's the coupling. I think it's actually mostly just in the atmospheric model. If the atmospheric model is responding incorrectly, it's shifting its wind response to the SST anomalies, say in ENSO, too far to the west, which is related to other errors, but that shift drives the SST anomalies to also shift to the west. But I think it starts in the atmosphere. Yeah. I'm not convinced the ocean model really matters, other than that it's kind of responding to that. It'd be something to look at, but at the very least, I wouldn't immediately assume that just looking at the atmospheric response, even on that quick time scale in the tropics, would not be useful in what you're doing. I think it very well might be.
Okay, yeah, we'll have to look at that more. As I said, we don't really understand that yet, so maybe that's an issue.
Right, looking at my clock, it is 3 o'clock Eastern time. Do we have any last questions for Siegfried before we sign off? All right, I think it's pretty quiet here, so I think we will end it. Thank you, Siegfried, for your presentation, and to Hailan for organizing today's talk. The next PPAI webinar will be on October 21st at the same time. So I will send out information once we have that secured. So we hope to see you then. And have a great rest of your day. And thank you guys for participating.